Hi guys, today we're going to learn about the Lagrange error bound or the Lagrange form of the remainder. You have that f of x is equal to a power series in x. So let's say that a partial sum is the sum of the first few terms of the series. Then the rest is going to be what we call the tail, okay? Which is the rest of the terms in the series after that partial sum. For example, if we have a partial sum of the first three terms, then fourth term and beyond, it's going to be the tail. Now, what we are going to learn today is that the remainder is the number you get by adding all the terms in the tail. So what we know is that f of x, which is the power series in x, is going to be equal to the partial sum plus the remainder. So what we're going to learn today also is that the error is going to be the error you make by assuming f of x being equal to the partial sum. So the error is going to be the same number as the remainder. Okay, an error bound is what we say that it's a number known to be greater. Please note that it's greater than the absolute value of the remainder. So in the past, we have seen this for alternating series. We know that if your series meets the three convergence hypotheses, then the absolute value of the first truncated term is going to be your error bound. On the other hand, we kind of saw this also for the integral test for convergence. We know that the improper integral will give you a value that will help you to find this error bound. Now, consider what Lagrange is credited with showing the Lagrange error bound. It's exactly kind of like the same that we saw in alternating series and integral test, but in a way different. Okay? Why? Because what we need is the first term of this tail. Okay? And we want the derivative not evaluated at x equals c, as we are used to, but at some other number, we call it z, which is between c and the value of x at which we are evaluating the function. As this value of z comes from the application of the mean value theorem, there's often no way, okay, for you to know exactly what's the value of z. But if we can find a number that it's an upper bound for the derivative between c and x, then we can find this famous Lagrange error bound. Okay? So how this formula looks like? Pretty much is going to be very similar to how we built a Taylor series or a Taylor polynomial. Okay? So the Taylor's theorem tells you that if a function f is differentiable through order n plus 1, meaning it has at least n plus 1 derivatives in an interval that contains c, for each x inside the interval there exists a number z between x and c such that f of x is going to be equal to f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c squared plus dot 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 plus you have that this is going to be the nth derivative evaluated at c divided by the n factorial times x minus c power of n. This so far, without that, it's not new to you. If you stop at n, we saw that as a polynomial degree n. If you have the plus dot dot dot, we saw that as the series, okay, the infinite power series. Now, with that plus r sub n of x, what we know is that this guy is going to be what we call the remainder, okay, r sub n of x. Now, what is r sub n of x? R sub n of x, according to Lagrange, is going to be equal to the nth plus 1 derivative evaluated at this famous number z divided by n plus 1 factorial times x minus c to the power of n plus 1. So, what's the business here? If you already remember your Taylor polynomial or Taylor series form, what you can see here is that it's pretty similar to the Taylor form. The only thing that it's going to change from each of these terms is that you are going to have a z here, so you need to be very careful with this guy, okay? Because that one is going to change the game plan here, okay? So one very useful consequence of Taylor's theorem is that r sub n of x is going to be less or equal than the absolute value of x minus c to the power of n plus 1 divided by n plus 1 factorial times the maximum, okay, of the nth plus 1 derivative evaluated at z, where this maximum of the nth plus 1 derivative evaluated at c is the maximum value of the nth plus 1 derivative between x and c. This will give you a bound for the error. It will not give you the exact value, okay, but that's enough for us to know that it exists, okay? So the bound is what we call the Lagrange form of the remainder, or most commonly known as the Lagrange error bound, okay? Now, let's look at some examples. The function f has derivatives of all orders for all real numbers of x. Assume that f of 2 is 6, f prime of 2 is 4, and f double prime of 2 is negative 7. Also, we have that f triple prime of 2 is equal to 8. So, write the third degree Taylor polynomial for f about x equals 2 and use it to approximate 2.3. Give 3 decimal places. Okay, so what are you going to do first? First, you're going to find your polynomial degree 3, okay, center at 2, okay, so you start with f of 2. F of 2 is 6 plus f prime of 2 is 4 times what? You know that that's going to be what? X minus 2, because that's the center, right? The 2. After that, you know that the third term is going to be based on the second derivative evaluated at 2, which is negative 7. X minus 2 to the power of 2 divided by 2 factorial, okay, and then we have that it's going to be plus 8 x minus 2 to the power of 3 divided by 3 factorial. So this is your polynomial degree 3, okay, but that's not it. They tell you, hey, use it to approximate f of 2.3. So I know that my polynomial degree 3 evaluated at 2.3, if I plug 2.3 here, here, and here, the calculator will give me that this is 6.921, okay? So you know that that is an approximation, okay? That's an approximation of f of 2.3. It's not exact, okay? So what we know is that the fourth derivative of f satisfies the inequality absolute value of the fourth derivative of x less or equal than 9 for all x's in the closed interval 2, 2.3. Use this information to find a bound for the error in the approximation of f of 2.3 found in part A. So what do you know? We know they are talking about a bound, so you do know that we want the remainder, okay, and we want sub 3, okay? So if you have that, well, you have that this is equal to, by the definition that we saw from Lagrange, is going to be the next derivative. Okay, so if this is 3, you want the fourth derivative evaluated at this famous z times x minus 2 to the power of 4 divided by 4 factorial. All this with the absolute value. Okay, so from here, what we know is that you are going to use this part. Okay, you know that this z is a number that it's between this guy. Okay, so the cool thing is that you have that the less or equal, then you replace this guy by the 9, okay, and then you have x minus 2 power 4 divided by 4 factorial, and this happens on the interval, when your x is on the interval 2, 2.3, okay. With that being said, that's great because you want to plug the 2.3 as your x. So what we have, using the 2.3, we have r sub 3 of 2.3, okay, is going to be less than the famous 9. I don't need the absolute value because I know that 9 is positive. And then you have that it's going to be 2.3 minus 2, which you know that it's positive, to the power of 4, divided by 4 factorial. Okay, we can have the absolute value here, but we don't need it because we know that all those numbers are positive. Okay. If I plug this in my calculator, when I plug it in the calculator gives me 0.003, okay, 0375, okay, and this is your error, as you can see, okay. So the error is going to be less or equal than 0.003. That's what we have. Okay? If we want to use my answer from A and B to find the interval A, B such that my f of 2.3 is in between the A and B, using 3 decimal places, what are you going to do? If we only use 3 decimal places, what you have is that your value is 6.921, right? So you know that this f of 2.3 is going to be bounded by something, up and down, okay? So 6.921 on this side and 6.921. But the error is, let's say, 3 decimal places. We take it here. So you know that here is going to be plus 0.003 and here is going to be minus 0.003. Okay? With this, okay, you just combine them. So you have 6.918 is less or equal than f of 2.3 less or equal than 6.924. Okay, so that's the interval that you have, and you have that f of 2.3 must be in between these two numbers, which is pretty good. If you see it, it's a pretty good approximation. Now the question is for D. Could f of 2.3 be equal to 6.22? Explain why not. And you compare 6.922, it is in between the interval, so this would be a yes, okay, because you know the 6.922 is inside this beautiful interval 6.918, 6.924. Okay, in the same way that you can see that f of 2.3, can it be equal to 6.927? And you are like, okay, so far so good, but this is too big. Okay, so since this is too big, it's a big no. Okay, and you know that it's because 6.927 does not belong to the interval 6.918, 6.924. Okay, so that's for this problem. Okay, so the next problem that we have over here talks about a function f of x being equal to 5x plus pi over 3, and they want you to compute the third degree Taylor polynomial for f about x equals 0. So technically speaking, this is a Maclaurin polynomial. Okay, so what are you going to do here? What you know is that f of x is going to be equal to sine of 5x plus pi over 3. Okay, so here I need more derivatives, right? So take the first derivative. When in doubt, take the derivative. You know that the derivative of that is 5 cosine of 5x plus pi over 3. The second derivative, you know that it's going to be negative 25 sine of 5x plus pi over 3. How do I know when to stop? Well, they want the third degree, so I need the third derivative. Okay, so here I have the third derivative, which is negative 125 cosine of 5x plus pi over 3. But that's not it. You have it centered at 0, so I want to evaluate each one of these derivatives, or original, whatever is the case, at 0. Okay, the good thing is that we know our unit circle, don't we? So you have that if you plug 0, this becomes a 0, so you have sine of pi over 3. What do you know? You know that sine of pi over 3 is going to be equal to root 3 over 2. In the same way that you know that you have 5 cosine of pi over 3, you know that cosine of pi over 3 is 1/2 times 5 is 5 over 2. And over here we have negative 25 root 3 divided by 2, because this is a 0, so you have the same as here, only with the negative 25 in front. And similarly here we have negative 125 divided by 2. Okay, so now we can build our polynomial degree 3. Okay, since I really like to put the degree there, polynomial degree 3. Okay, so you have that it's going to be equal to root 3 over 2. Okay, plus 5 divided by 2, and it's going to be x because it's x minus 0 because you are centered at 0, okay? Then you have that it's going to be minus 25 root 3 divided by 2 times x squared divided by 2 factorial, and then minus 125 divided by 2 times x power 3 divided by 3 factorial, okay? And this is my polynomial degree 3, and with this we have p of x, okay? This is your p of x. Cool? Okay, now let's move on to part B. They tell you, hey, use the Lagrange error bound to show that f of 1 over 15 minus p of 1 over 15 is less than 1 over 1200. Okay, so for the polynomial that we use, we call it sub 3, so let's call it sub 3 there. Okay, so if that bothers you, go for it. Okay, so what you know is that this notation might look a little bit funky, but you are like, I know better. I know that this is the same as r sub what? Sub 3 of 1 over 15. Okay, so you know that that's the same. So by Lagrange, I can find this guy. So let's start from scratch. I can find r sub 3 of x, okay, using the Lagrange, the theorem, okay? So you have that this guy is going to be equal to the fourth derivative evaluated at z of what? X minus 0, right? Let's put it so you understand, okay? To the power of 4 divided by 4 factorial. Do you agree with that? So hopefully you do, okay? So that's the absolute value. You know that that should be bounded by something, right? Bounded by something. But you're like, well, I don't know much about this. Well, let's see if we can find out. This is the third derivative. They want me to find the fourth derivative. So let's take the fourth derivative. The fourth derivative of this equation of x is going to be equal to 625 sine of 5x plus pi over 3, okay? You have that, okay? And you're going to tell me, now what? I have no bound. Well, you do know how to find the bound, but you haven't realized. In precalculus, you learn a lot about the sine of x. You know that sine of x is bounded by really nice numbers. What are those numbers? 1 and negative 1. Why we know this? Because the coefficient here of the sine of x, of the parent function of sine of x, is 1. What's your coefficient here? Well, it's 625. So what we know is that, and in addition you have this, but that one doesn't matter for the bound if you remember from parent functions. So you know that this is bounded by 625. Cool? So now, what are you going to do? Well, I know I have this, so I know that 625 is going to be my bound, and that's going to be x, okay, to the power of 4 divided by 4 factorial. Okay, if you want, you can put the absolute value there to make sure that it's not negative. Okay, now, what do you recognize here? Well, we have this in general for x, right? But you want 1 over 15. Well, let's just plug 1 over 15. Okay, so you have r sub 3 of 1 over 15, okay, absolute value. That's going to be equal, okay, less or equal to 625 times 1 over 15, okay, to the power of 4 divided by 4 factorial. And I took out the absolute value here because I know that this is positive, and this is positive. So there's no need for the absolute value there. In addition, if you want to simplify because you are like, well, I don't know if that's true because I want to prove that this is less than this, right? Well, let's simplify it a little bit. You know that 625 is 5 to the power of 4, right? Then this, you have a 1 to the power of 4. Then the 15 goes down to the power of 4 times the 4 factorial. Cool? And you are like, well, I'm not sure. Well, break out the 15. What's 15? 5 times 3, right? So, you know that by properties of exponents, we can do this no problem, right? So you cancel this, so this is going to be beautiful because you know that that 3 to the power of 4 is 81 and that 4 factorial is what? 24, Okay, so you know that one for sure is going to be less than 1 over 1200. Okay, and this is all true, okay, by the Lagrange, okay, error bound. And that's pretty much it. You prove that this error was smaller than what they were giving you. I hope that you find this video helpful. Bye!